All right. So let's start from where we left off. We considered this game where player one has two actions top and bottom, player two has two actions left and right, and we wanted to find all possible mixed strategy Nash equilibria. Um, the way we do it is again by assuming that player one chooses P with a probability P, and so this T with a probability P, and therefore chooses B with a probability 1 minus P, chooses L with a probability Q, and R with a probability 1 minus Q, right? Um, we found three mixed strategy Nash equilibria. So I'm not going to go over the method again just now, but I'll do a different example after this. But the three mixed strategy Nash equilibria we found were ones in which P and Q were 0, 0, 2/3, 1/3, and 1, 1. Okay. So what does that mean? I think I glossed over it. I did mention it in the previous lecture, but just want to make sure that we're all on the same page. So our MSNE or mixed strategy Nash equilibria take the form P equal to 0, Q equal to 0, which means T is played with the probability 0, which means B is played with the probability 1, and L is played with the probability 0, which means that R is played with the probability 1. So this is the same as the pure strategy Nash equilibrium BR. Another one we found was P equal to 1, Q equal to 1, and over there we had P equal 1 means L is played with the probability 1, Q equals, sorry, this is a T, and this is an L. Right, so this is the same as PL. Then there's this third one in which P equals 2 by 3 and Q equals 1 by 3. And so this is the new thing that we found when we considered mixed strategies. That means that top is played with a probability 2/3, and therefore bottom is played with a probability 1/3. Left is played with a probability 1/3, and right is played with a probability 2/3. And the reason that players mix in this particular manner is in order to keep the other player indifferent. So player two is choosing this mix of 1/3, 2/3 in order to make player one indifferent between top and bottom, and player one is choosing 2/3, 1/3 for top and bottom in order to keep player two indifferent between left and right. Because that's how you'll have stability, that's how you will have an equilibrium. Okay, I also mentioned that this was symmetric. So if you look at the expected utilities of players, player one can expect to earn let me just use the highlighter. So player one can expect to earn this 2 with a probability of 2/3 times this 1/3, and this 1 with a probability of 2/3 times this 1/3. And so you have 2 by 3 times 2 over 9 plus 1 by 3 times 2 over 9. Oh, sorry. 2 times. Okay. Let me just do this again. So let's write out the probabilities first. So the light green ones are 2 by 3 times 1 by 3 times the payoff, which is 2, plus 1 by 3 times 2 by 3 times the payoff, which is 1. So that becomes 4 divided by 9 plus 2 divided by 9 equals 6 divided by 9, which is equal to 2 by 3. Okay. If you do the same exercise for player 2, you'll find that player 2 earns this unit 1 with a probability again of 2/3 times 1/3, and this 2 with a probability of 1/3 times 2/3, which will again lead to the exact same number of 2/3. Right, so in that sense, this is a much more symmetric equilibrium because both players, they're mixing and they're also earning the exact same amounts in equilibrium. Whereas when we were looking at pure strategy Nash equilibria, we had equilibrium in which the payoffs were asymmetric, right? Either player 1 is happy or player 2 is happy. Here they're both equally unhappy, getting a utility of 2/3 each. Okay, let's do one more example of a game in which we'll find a mixed strategy Nash equilibrium. Okay, so this game is called Matching Pennies. And it's essentially a 2-action version of rock, paper, scissors. The idea in this game is that we have top, bottom, left, right. Player 1 will gain if they both choose the same action. So normally the actions are written as tails, heads, tails, heads. And player 1 gains if they choose the same action, and player 1 loses if they choose different actions. Player 2 gains if they choose different actions, and player 2 loses if they choose the same action. Right, so let's say I'm player 1, you're player 2. If we both choose tails or if we both choose heads, then I win. If we choose different numbers, then I lose and you win. Right, so every time I win, you lose. Every time you lose, every time I lose, you win. Okay, but instead of tails and heads, I just prefer to use left and right here, top, bottom, because then that's just easier to see the actions of players. Okay. So what do I want you to do? I want you to suppose that P1 loses top with probability P, and player 2 loses left with probability Q. Okay, so I have P here, Q here. Naturally, this will be 1 minus P. Naturally, this will be 1 minus Q. And of course, this should be an R and not a B, left and right. Okay. Calculate the expected utilities of each player from each action available to them. Okay. Once you have that, you'll be able to write out the best responses. Because again, no matter how we set up the game, the way to solve it remains exactly the same. The way to solve it is you figure out your expected utilities. In this case, there'll be 2 different expected utilities for each player because they have 2 different actions available to them, and you want to figure out which action is better. Then you use that to find players' best responses. And then once you have those best responses, you can just graph them or look at the best response functions to figure out where those best responses will overlap with each other. And that's where you will have a Nash equilibrium. Yeah. Um, I'll just stop here. Okay, find all MSNE. Okay, what does this first part mean? This means the same thing as finding the expected utility that player one gets from choosing top when player two mixes with the probability Q, expected utility of player one from choosing bottom when player two mixes with the probability Q, the expected utility of player two when player two chooses L and player one mixes with the probability P, and the expected utility of player two when player two chooses R and player one mixes with some probability P. Okay. This will answer part A of the question. This is what helps us figure out which action is more valuable for each player. Okay, let's go back up here. Okay, so for player one, when player one chooses P, or when player one chooses T as in top, and player two mixes with the probability Q, player one gets this one with the probability Q, and this minus one with the probability 1 minus Q. Okay, so we have here 1 times Q plus minus 1 times 1 minus Q. Just open the bracket, you'll get 2Q minus 1. When player 1 chooses B, player 1 gets this negative 1 with the probability Q, and this 1 with the probability 1 minus Q. And so you get negative 1 times Q plus 1 times 1 minus Q is equal to 1 minus 2Q. Similarly for player 2, when player 2 chooses L, player 2 gets this negative 1 with the probability P and this positive 1 with the probability 1 minus P. So negative 1 times P plus 1 times 1 minus P is equal to 1 minus 2 times P. When player 2 chooses right and player 1 mixes with the probability P, then player 2 gets 1 with the probability P, negative 1 with probability 1 minus P. And so player 2 gets 1 times P plus minus 1 times 1 minus P. Okay, so for player 1, when is the expected utility of player 1 from choosing top greater than the expected utility that player 1 gets from choosing bottom? Right, so which simply means when is two Q minus 1 greater than 1 minus 2Q. Add 2Q on both sides, you get 4 times Q minus 1 greater than 1. Add 1 on both sides, you get 4 times q greater than 2. Divide by 4 on both sides, you get q greater than 1/2. Okay, so when q is greater than 1/2, then player 1 would prefer to choose t all the time, which means p equals 1. And just write out that player 1's best response function. So this is BR1 as a function of q. So when q is greater than 1/2, player 1 chooses p equals 1. It also means that when q equals 0 and q is less than 1/2, we can figure out what we need just by changing this sign, right? So when q is equal to 1/2, these two things will be equal. So I can choose any p in 0, 1. As player 1, I would be indifferent between choosing top and bottom when player 2 is mixing with the probability 1/2. So this is the equivalent of me saying that when your opponent in rock, paper, scissors chooses rock with probability 1/3, paper with probability 1/3, and scissors with probability 1/3, you're indifferent. You can choose any of those three options, and your payoff will be exactly the same. Um, so you yourself could choose rock with any probability, paper with any probability, scissors with any probability, and that would be a best response. And again, similarly, if I want this less than, then q should be less than 1/2. So that would give me p equals 0. Right? P equals 0 because the expected utility from t is less than the expected utility from b, so player 1 will only choose b and not choose t at all, which is the equivalent of saying p equals 0. Okay. Let's do the same thing for player 2. So for player 2, the expected utility of player 2 from choosing left given p is greater than the expected utility from choosing right given p. If and only if 1 minus 2p is greater than 2p minus 1. Adding 2p on both sides, I get 1 greater than 4p minus 1. Adding 1 to both sides, I get 2 greater than 4 times p. Dividing by 4 on both sides, I get 1/2 is greater than p, right? Or p is less than 1/2. And so you have this best response function. When p is less than 1/2, I would always choose q equals 1 because my expected utility from left is greater than my expected utility from right. When p is equal to 1/2, I can choose any value of q between 0 and 1. And when p is greater than 1/2, then I would choose q equal to 0. Okay, so this is how we write our best responses. The player here has a continuous choice, right? The player can mix with any probability between 0 and 1. But if one action is giving him strictly more utility, then as you'd expect, the player will put all of their probability weight on that action. So the only way that a player mixes between two actions or chooses two actions, each with positive probability, is when both of those actions give the player the exact same amount of utility. Okay. Let me pause here for a minute. Okay, so now we have our best response functions. All we need to do is plot them out. in order to figure out where they overlap, and where they overlap, we will have our Nash equilibrium. Okay, so let's make a graph, and let's start with BR2 E versus P. Okay, this is going to be between 0 and 1, 0 and 1, and something's probably going to happen at 0.5. Something's probably going to happen at 0.5, because that's where the switches seem to be happening. Okay. All right. So when P is between 0 and a half, the optimal Q is 1. So P equal to 0, Q equal to 1, P equal to 1 half, Q equal to 1. All of this is fine. When P is a half, then Q takes any value between 0 and 1. So P equals a half. Any value of Q is optimal. And when P is greater than a half, then Q equal to 0 is optimal. Okay, so this is how we drew the three parts of the curve. Okay, so this is this part. This is this part. And this is this part. Okay. All right. Now let me just copy paste this because it's easier to see. That's right there. Copy and paste it down here. And this should say 1 half. Okay, let's start with the first line. When Q is less than 1 half, let's say 1 half. When Q is less than 1 half, then P should be 0. So when Q is less than 1 half, so when the y-axis is less than a half, the x-axis term has to be 0. Because I want to draw BR1 of Q on the x-axis and Q on the y-axis. When the y-axis term Q is equal to 0.5, 0.5, then P can take any value between 0 and 1. And when the y-axis term is greater than 1 half, then P should be equal to 1. Okay, there's no Nash equilibrium at this corner, no Nash equilibrium at that corner. All you have is a Nash equilibrium that's right in the middle. Okay, so this is our Nash equilibrium in mixed strategies. So it's an MSNE, and it's one in which T star, Q star equals 1 half, 1 half. Okay, and just to flag this, I think I made a couple of typos earlier with regards to these two numbers. Okay, so they should both be a half, because a half is where all the switches are. So I think I wrote a 1 and a 0 there earlier, so please make sure you go back and fix that. Sorry about that. Okay, and so if you look at this game, there was no mixed strategy Nash equilibrium in which players play zeros and ones, choose actions with probability zeros and ones. And the reason for that is, again, if you don't find a mixed strategy Nash equilibrium in which players play pure strategies, then that must mean that there is no pure strategy Nash equilibrium. Because if there was one, you would have found it as a mixed strategy Nash equilibrium. Right? And we can verify this. If player 2 chooses L, player 1's best response is T. Player 2 chooses R, player 1's best response is B. Player 1 chooses T, player 2's best response is R. Player 1 chooses B, player 2's best response is L. There's no cell in which both players um, are choosing are best responding to each other. So you don't have any cell with stars on both numbers, which means that there isn't a pure strategy Nash equilibrium here. Okay. So now we've done another example of a 2x2 game in which we can find all the mixed strategy Nash equilibria. Here, the MSNE is the set that is PQ equal to, or let me define it like this, PQ equal to 1/2, 1/2. If there was something else here, I would add it, but there isn't. So I can put a star to make the P's and Q's feel special. Okay, um, that's video number 1. I'm gonna stop this for now, and then I'm gonna record more videos. See you.